3.9, number 346. We have a very special type of function, y equals x to the root x. So this is called a tower function because the base is a variable and the exponent is also a variable. You haven't encountered a function like this before in our problem sets. Base and exponent, both variable. They're both functions into themselves, you might say. As opposed to what? Normally, if the base is constant and the exponent is variable, then that's some kind of exponential function like we saw in this section. If the base is a variable, but the exponent is constant, then that's a power function we've encountered long before. Both of these have rules to take care of them. In this case, the tower function, there's no particular rule. There's no derivative rule per se. For differentiating a tower function. So we're going to use a special methodology called logarithmic differentiation. So a special method, it's not just differentiating a logarithm. It's different. It's a whole methodology that applies to a wide array of functions. I am picking a function where it is necessary to use this technique we're about to show. Other functions, for example, functions involving products, quotients, and powers these types of functions, it can be very useful to use logarithmic differentiation to find their derivatives. But the tower function, specifically, it is necessary. There's no other way, you might say, to find this derivative. So it's necessary to use logarithmic differentiation. So the problem set has two different types. It has a bunch of tower functions, which there's no other choice but to use this technique I'll show in one moment. And then there are other functions which are not necessarily tower, but they have products, quotients, and powers. And it's useful to use logarithm differentiation on these problems because the logarithm has properties involving products, quotients, and powers. Allow you to simplify the whole thing first before you take any derivatives. Anyway, proceeding with this one, it goes like this. Since I have a function raised to a function, if I apply the logarithm to this expression, I'll have the leniency to use the property of logarithms. Which property is it? It is the power to coefficient property. It looks something like this. So the natural log of, I'll use r, of r to the b, okay, is the same as b times ln of r. As long as there's some kind of exponent or power on the argument of the logarithm, I can remove that power down to the outside as a factor or a coefficient to the logarithm. And this is one of the three main properties of logarithms that you certainly discussed in pre-calculus. So that's what we're using here. This is the reason we're using the logarithm at all. So if I apply the logarithm to both sides, then I can now use the property of logarithms to remove this power that's on the argument down as a coefficient on the logarithm. So this will now read as ln y equals root x ln x. So with the use of the logarithm, I've been able to change this tower function into a product function, which we have regular derivative rules for. So we should be able to find the derivative now. But it involves a little bit of implicit differentiation. Okay. Because we know that y is a function of x, we have it explicitly here, but down here now it's implicit how y is a function of x. So when I take the derivative now of both sides, I'll apply the d dx operator to both sides. So I'll have d dx applied to the natural logarithm of y, not of x, equals d dx applied to this product function, which should be relatively easy to take. They're actually both quite easy, and the left-hand side always turns out this way. It's always the derivative of ln y, which will be, as we mentioned before, the derivative of the argument over the argument. So you'll have dy dx over y on the left-hand side. And then on the right-hand side, in this particular case, because of the function we're dealing with, we'll have the first times the derivative of the second plus the second times the derivative of the first. All right. So now, all I need to do is multiply both sides by y to get dy dx by itself. So we have the derivative of the original we've now solved for in this very simple equation that involves a derivative. We're just moving this piece over here to join the right-hand side, thereby isolating dy dx, the object we were looking for. We have root x on x, which is, of course, let's simplify this a little bit as we go here, 1 on root x plus ln x on 2 root x, and that's times y. Now, I'm going to go ahead and simplify the interior of this parentheses a little bit more, but the main point at this stage is y here we know. Even though we used implicit differentiation at some point in the problem, we actually have y explicitly as a function of x back here. So at the end of the problem, we should replace any y's we see with this explicit expression containing x. So one small simplification of this interior here, I have dy dx equals 2 plus natural log of x on 2 root x times y, but y we know to be from the beginning x to the root x. So there we have our derivative finished off, and in all these problems with logarithmic differentiation, should be able to write the final derivative solely in terms of x at the end, because you had y as a function of x from the beginning.